All right, this is calculus and inverse functions, and actually I'm going to make a connection between functions and inverse functions and derivatives. That's kind of where I'm heading with this, and so this is section 5.3 of our particular book, and what I have here is I have a simple function, and it's simply a set of ordered pairs. You can see for every x value there is one and only one y value, so it's a function. And what I have here is I have the notation for an inverse, which is that f with that minus 1. And I'm going to write the inverse of the function. And the definition for the inverse of a function is, make sure I have my brush palette here because I did do some changing, is that there is an exchange of the domain and range. And in inverse, what was the domain now becomes the range. So each of these values become output values. Or what we say is they become our y values. So over here I'm going to have a 1, over here I'm going to have a 5, over here I'm going to have a 6, and over here I'm going to have a 7. And my range values become my domain values, so they switch. And so this ordered pair becomes 4, 1. This ordered pair, oops, I wrote a 2 here, and I meant to write a 5. Excuse me, I wrote a 5 there, I meant to write a 2. And so it's going to be 5, 2, and I can see I did the same thing here. This should be a 3. And then this x value will be a 6. And likewise, this should be a 4. And this x value should be a 7. So my ordered pairs become 4, 1, 5, 2, 6, 3, and 7, 4, which is just the reversal of these coordinates up here. And so that's example 1. In example 2, I give you a function f of x, and it's equal to 2x minus 1, and I want to find its inverse. So symbolically, what I'm going to do is exchange the x's and y's. I'm going to write the y here, y equals 2x minus 1. And I'm algebraically going to exchange them. They're going to reverse places. And now I'm going to solve for y, so I'm going to get x plus 1 equals 2y. And then I'm going to divide by 2, so I'm going to write this as 1/2 times x plus 1 equals y. And so I'm going to write this down as 1/2 times x plus 1. Okay, so that's my inverse. And I can put some values in here. So if I have f of x is equal to 2x minus 1, and I put a 3 in here, I'm going to have 2 times 3 minus 1, and I get a 5 as an answer. So I have the point 3, 5. And if I put a 7 in here, I'm going to have 2 times 7 minus 1, and I'm going to get 13. So I have the point 7, 13. All right. In this inverse, what should happen is these corresponding coordinates should interchange. So I'm going to have 1/2, and what I'm going to do is I'm going to put 5 in here because that's my y value. So I got 5 plus 1, and that's going to give me 1/2 times 6, and I get 3. So my ordered pair here would be 5, 3. Again, this is the inverse. If I put 5 in there, I get 3 as my answer. So if I put 13 into this inverse, I should get 7 as my answer. So I'm going to have 1/2 times 13 plus 1, which is 1/2 times 14, and I get 7. So you can see it's an inverse. Another way I can check an inverse, which is the next page on the notes. Oh, excuse me. I'm going to graph both of those. Let me put this back up here. F of x equals 2x minus 1, I believe. And the inverse of x was 1/2 parentheses x plus 1. And I'm going to graph those. I'm going to go to my graphics calculator. delete this. I'm going to have 2x plus 1. And then I'm going to have 1/2. I'm going to call it 0.5. And I think the top one's supposed to be x minus 1, so I'll change that. Let me change this. Okay, let's draw. Okay, and so there's my graph, and I'm going to put in one more equation in here. I'm going to put down the equation x equals y, or y equals x. So I'm just put x in here. I'm going to draw this. And you can see this blue line. The red line is just the blue line reflected. So this is my inverse, the red line. And the blue line is my original function. And so it's reflected over the equation y equals x. So now I'm going to come back and I'm going to take a look at the next example. And what it is when I do a composition, and so if I compose these, so if I put the inverse into the function, and that's f compose f inverse. That's what this is. What I would have is 2 parentheses, and I'll use a bracket here. 1/2 times x plus 1 minus 1. Okay, so this is where my x was. I take 2 times whatever I input and I subtract 1. Well, if I do that, inside here I'm going to have 1/2 x plus 1/2 minus 1. And so now when I distribute again, I'm going to have x plus 1 and drop the brackets minus 1, and I get x. And if I compose this, if I have f inverse compose f, that means in my inverse I'm going to have 1/2. Again, I'll use brackets. And inside here I'm going to have 2x minus 1 plus 1. So this right here, that's what got slotted in its place. Okay, so now what I'm going to do is inside this bracket first. So I have 2x minus 1 plus 1. It gives me 1/2 times 2x, which again is x. So if that happens, where I compose both ways and get x as my answer, that's the proof that they are inverses of each other. Let me try another one. Let's say I have this, f of x equals 2x cubed minus 1. And I have this other function I'm going to call g of x. And I'm going to have the cube root of x plus 1 over 2. So I'm going to do f compose g of x. And so that's going to be 2. Again, I'm going to use this bracket, the cube root of x plus 1 over 2. That thing cubed minus 1. So that gives me the cube root and the cube simplify to this. X plus 1 over 2 minus 1. And then these simplify, and I'm left with x plus 1 minus 1, and I get x. So we have to do it both ways, because there are times in which it composes to x on one side but doesn't on the other. So here is g compose f, and that means f of x is going to be put in this time. And so that's going to be the cube root of 2x cubed minus 1 plus 1, all that over 2. So that's going to give me the cube root of 2x cubed over 2, which is the cube root of x cubed, which is x. And so in both cases, I get these values, so these are inverses of each other. All right. The next one is this particular question, and I'm going to graph it. And I'm going to change my window first. And I'm going to go from negative 2 to 2, negative 2 to 2. And let's delete these. And I'm going to put this equal, oops, I got one more I got to delete. Green sometimes hard to see. Alright, and I'm going to put in this x cubed plus x minus 1. I'm going to draw that. Okay, so that's what my graph looks like. And so the question is, does its inverse, is it a function? Well, if you remember from a function, we have a vertical line test, that if we can draw vertical lines up and down, and it doesn't passes, that means that particular graph is a function. But we have something called the horizontal test, which is, oops, I'm going to have to make this smaller so I can write this. You'll let me do that. There you go. Oops, I didn't want to make it disappear. Alright, so if you take a look, I have something called the, maybe I need to make this smaller, the horizontal line test, the HLT. Again, I'll call that horizontal line test. And what's the purpose of that is, if I draw a function and horizontal lines go through, well, that means its inverse is also a function. So if I give you another one, let's just exit here. And let's put in x squared, and I think this will show this. This would not, even though it's a function, if the vertical line test works, if I draw horizontal lines, it doesn't pass that because it goes through two points. So its inverse, if I reflect it over the equation y equals x, its inverse would not be a function. So a horizontal line test lets us know whether our functions have inverses that are functions. Alright, let me delete this, and I'm going to go on. And the other part of this, draw, is if you take a look at this, so this means inverses are functions. That's one. Now, secondly, if I take a look at its derivative, this function is f is always increasing. I mean, there's no turning around point. As soon as I turned around, its inverse would be a function. So in this case, f is always increasing. We call that strictly monotonic. Or f is always decreasing. Either one of the two. Either it's always dropping or it's always going up. If f is always increasing, I'm going to change the color here. Change it to purple. That means f prime here, if f is always increasing, f prime, the derivative is always positive. Over here, if f is always decreasing, it means f prime, the derivative, is always less than 0. I'll give you an example of that. Again, I'm going to change my color palette. Oops. My color palette here back to black. If I have, here's my example. If I have the equation f of x is equal to x cubed plus 1, and I take its derivative, x squared, I have 3x squared as its derivative. Well, this derivative, those values, always have to be greater than or equal to 0. Because unless I put 0 in there, any other value I'm going to have here is positive. So I've accepted 0 where I have an inflection point here. This function is increasing during the entire interval. That means it's strictly monotonic. Now if I had something like this, where f of x equals x cubed minus x squared, its derivative is equal to 3x squared minus 2x. And if I made that equal to 0, and I can factor out an x here, I have 3x minus 2. At 0, and at x equals 2/3, I have turning around points. So if I pick a value between here, like a half, if I pick a half in here, I'd get 3/4 minus 1. It'd be negative. So between this interval, it's dropping. Let me show you what I mean. I'm going to graph this. And I'm going to put in x cubed minus x squared. I'm going to draw that. Okay, and if you take a look here, right here it's decreasing. So if I did a horizontal line, if I zoom in here, let's see if I can zoom. Right there. If I draw a horizontal line within that interval, okay, I'm not going to pass the horizontal line test. So the inverse of this particular function is not, its inverse is not a function. F is not monotonic. It's not always increasing or not always decreasing. All right? And so on this things that strictly monotonic means it passes a horizontal line test, which means the function is the inverse. There's one last thing I want to talk about when I talk about this, and I'm going to get rid of this. Is the idea 3 that the function is 1 to 1. That means for every x there is exactly 1 y, and for every y there is exactly 1 x. So they are 1 to 1. And if I take a look at this, if I put values in here, let me go to this one where I had x cubed plus 1. If I come up with values and I put 0 in there, I'll get 1. So this x only has one value. If I put 1 in there, I'll get 2. If I put 2 in there, I'll get 9. Okay, its inverses are going to be 1, 0, 2, 1, 9, 2. And so for every x value, these two numbers are 1 to 1. These are the only pairs that are going to match up. That means these things, horizontal line test is passed. The inverse is our function. The function is strictly monotonic. Its derivative is either always positive or always negative. Those mean the same values. All right. The last particular thing I want to talk about in these notes, and I know these notes are getting long, but just bear with me. I want to look at this particular thing. I want to look at f of x equals 2x minus 1. And I want to look at its derivative. And in this case, its derivative is 2. And over here, I'm going to look at its inverse. And its inverse is 1/2 x plus 1, which is the same as 1/2 x plus 1/2. So if I take a look at the slope of this inverse, which is sometimes written this way, it's kind of goofy, it is 1/2. And what I want you to notice are these slopes are reciprocals of each other. So let's look at another one. F of x equals x squared. Its derivative is equal to 2x. The inverse is going to be the square root of x if I'm just looking at y values that are greater than 0. And its derivative, again, this is the notation for that. Inverse derivative of x is equal to 1 over 2 times the square root of x. Alright, so if I come up here and I pick a value, let's pick 3, 9. That's a value that's in here. So that means its corresponding value is 9, 3. In other words, if I plug 9 into here, I get 3 as a result. Alright, so if I plug 3, the slope of the tangent line in this case is going to be 2 times 3, which is 6. So the equation of my tangent line is going to be 6 times x minus 3 plus 9. Over here is going to be y is equal to, now if I put 9 into here, square root of 9 is 3, 2 times 3 is 6, I get 1/6. I get that reciprocal. Notice they're reciprocals. My slope is 1/6, and I'd have x minus 9 plus 3. All right? Now, let's take a look at the next problem on this. The next problem, and this is the last one I'm going to do in these notes, says I have something like this. I have f of x equals 1/4 x cubed plus x minus 1. And I want you to first find what f inverse of 3 is. Well, that means it's the x value on the inverse, it's the y value on the function. Again, it's the y value on the function. So I need to figure out when this is true. Okay, what x value do I get? I get 3. Well, if I solve, one way I can do this is I can solve for this. And then I can get rid of the fraction by multiplying everything by 4, and I get x cubed plus 4x minus 16 equals 0. Well, if I plug 2 in here, 2 cubed plus 4 times 2 minus 16, this is 8 plus 8 minus 16. Sure enough, I get 0. So this equals 2. Over here, if I plug in 2 into this, I'll get 3. Notice I have 1/4 times 2 cubed plus 2 minus 1. This is 8. 1/4 of 8 is 2. 2 plus 2 is 4. Minus 1 is 3. And over here in the inverse, if I plug 3 into that, I'll get 2. Then my next question is, all right, now watch the notation. The inverse the derivative of 3. Okay, what is that? Well, I don't even have a function. I can't, it's very extremely difficult to take and figure out what the inverse of that is. But I don't need to figure out the inverse. What I can do is take the derivative of x, which in this case is 3/4 x squared plus 1, and I can plug into it. Now you got to be careful on this. I got to plug into that 2, because the corresponding point over here is 2, 3. The support corresponding with the inverse is 3, 2. So if I plug in 2 here, I'm going to have 3/4 times 2 squared plus 1, which is 3 plus 1, which is 4. So the slope of the tangent line on my function at 2 is 4. Over here, what's it going to be? I don't even know the function. And at 3, it's simply going to be the reciprocal of this number. It's going to be 1/4.